Welcome back to the Deep Dive, where we take complex, challenging domains and, well, we break them down into digestible, highly useful insights.
Hmm.
Today, we are strapping in for what is, I think, perhaps the most essential foundational topic in modern operations: DevOps and management.
It really is.
This is the mechanism that turns lines of code into running scalable applications. And if you are just starting your journey into the cloud, this is probably the most important hour you can spend.
It truly is. And we're going to spend the next 30 to 40 minutes establishing that foundational understanding, the 0 to 60 of deployment strategies.
Right.
DevOps, at its core, is a culture, a philosophy, and a set of practices that enable the faster, more reliable delivery of applications and services.
And we're not just covering specific tools, right? We're explaining the why.
Exactly. The why behind every critical choice, focusing purely on this DevOps and management domain.
Absolutely. Our mission today is to show you how to move beyond the manual operations and into a world where infrastructure is built perfectly every time. We are going to cover the big three: infrastructure as code, or IAC, continuous integration and continuous delivery, CI/CD, and all the specific best practices that ensure stability, security, and auditability.
Yeah.
If you've ever felt overwhelmed by the sheer number of tools required to manage a modern cloud deployment, this deep dive will give you that navigational map.
Let's get into it.
Okay, let's unpack this with a relatable frustration that I think everyone experiences when starting out.
Oh, yeah.
The problem with manual work, the clicking, the typing, the reliance on an individual setup. Imagine you are managing several critical projects on Google Cloud. You're constantly interacting with services like BigQuery, Bigtable, and Kubernetes Engine using the main command line tool, the GuideCloud CLI.
And here's the scenario that breaks every workflow. You're traveling, maybe you're jumping between your desktop, a laptop, and a Cloud Shell session at a client site. You suddenly realize that your laptop's version of the uCloud CLI is 3 months out of date.
Oh, the worst.
Or maybe the service account credentials you updated on the desktop haven't been copied over. It happens all the time.
Exactly. You just introduced a concept called configuration drift, where your local setup just doesn't match what the production environment expects.
Yeah.
You might be running a command that works fine for you, but it breaks for the colleague sitting right next to you simply because their local environment is subtly different.
It's an operational nightmare.
It is. It's built on human memory and individual workstation configuration.
And the problem isn't just the inconsistency. It's the sheer waste of engineering time. I mean, every moment an engineer spends updating configuration files, installing SDKs, or debugging why a CLI command that worked yesterday is failing today.
Because they updated their OS or something.
Exactly. That's time not spent building features. And our sources really identify this reliance on manually managing the uCloud CLI across multiple workstations as just a huge source of operational friction.
So the immediate solution, the very first step toward automating your environment and achieving that fundamental consistency, is to standardize the workspace. The answer, which is often right in front of you when you open the console, is to use Google Cloud Shell in the Google Cloud Console to interact with Google Cloud.
This often seems too simple to be a best practice, but it's such a critical piece of infrastructure. Cloud Shell provides a standardized, persistent environment right within your browser.
Like a virtual desktop.
Yeah, think of it as a virtual desktop that's preloaded with every tool you could possibly need.
So what are the key benefits for the person listening right now who might be struggling with managing their own local environment? What does this solve for them?
Well, it solves the 3 big problems: consistency, persistence, and security.
Okay.
First, consistency. You always have the necessary tools installed and running the correct versions. You just eliminate configuration drift from one workstation to the next. Second, persistence. Your home directory and your configuration files, they persist across sessions. You can close your laptop, fly across the country, open a new browser, and your environment is exactly as you left it.
That's amazing.
And finally, security. You avoid installing, managing, and securing sensitive service account keys or credentials on all these different local machines, which are, often less secure than the cloud provider's managed environment.
Right.
It sets the baseline consistency required before we can even talk about real automation.
That initial step of standardization is so crucial. We've eliminated the friction of the individual workstation. Now we can move on to applying that same principle, not just to the console, but to the actual cloud services we deploy.
Exactly.
And once we stop relying on inconsistent manual configurations, we arrive at the central pillar of modern DevOps, infrastructure as code, or IAC.
Yes.
You mentioned earlier that if the application we're building is the final structure, IAC is the detailed, perfect blueprint. Let's really expand on that analogy for our listener.
It's the perfect analogy. When you build a house, the blueprint details every dimension, every material, and the precise order of operations. You don't just tell a contractor, hey, put a wall there.
Right.
You hand them a detailed, machine-readable document, the blueprint. IAC is exactly that for your cloud infrastructure.
So instead of going into the Google Cloud Console and manually clicking Create VM, then configure networking, then set up firewall rules, I write a single file that does all that.
You write a single machine-readable file that defines all those steps simultaneously. Precisely. IAC is the practice of managing and provisioning your infrastructure networks, VMs, databases, load balancers through these definition files.
And these are just text files.
Yeah, they're often written in languages like YAML, JSON, or Python, and they're stored in version control, like Git, just like your application code.
And we are focusing on specific tools that embody this concept. Google Cloud Deployment Manager is an example of an IAC solution. Why is it so essential to use a tool like this? Why can't a company just, keep track of the steps in a Word doc or a wiki?
Oh, that's a recipe for disaster. It boils down to two things that manual operations simply cannot guarantee: auditability and repeatability.
Okay.
When you click, you rely on human memory and settings that can change, and the only evidence of that change is often a vague log entry. When you use IAC, you rely on a definition file that is versioned.
So if I update my infrastructure, my code repository tracks that change with a specific commit hash, just like my application code.
Exactly. And this allows you to ensure that production deployments are linked to specific source code commits and are fully auditable.
So if a networking rule breaks production at 3 a.m.,
you can instantly look at the IAC file's history, find the commit that introduced the rule, who approved it, and when it was deployed. That traceability is, it's non-negotiable for stability and compliance.
that makes the technical case very clear. But let's look at the business case, because adopting IAC isn't trivial, is it?
Not at all.
If a company has been running things for years, say, they have a lead engineer who wrote some custom script 5 years ago that deploys all their VMs in a legacy data center, advocating for a migration to a modern IAC tool like Cloud Deployment Manager, that introduces friction.
Organizational friction, yeah. And business risks. Our source identifies two very distinct risks associated with this kind of migration.
And this is important because DevOps is about people and budget as much as it is about tech.
Right. So when migrating from a legacy custom tool to a modern IAC solution, you encounter, first, the skills gap risk.
Okay.
Cloud Deployment Manager is unfamiliar to the company's engineers. This requires a substantial investment in time and budget for training and upskilling. Engineers are specialized, and suddenly asking network engineers to become proficient in declarative YAML files requires resources.
And the second risk?
The platform lock-in risk.
Ah.
Cloud Deployment Manager only supports the automation of Google Cloud resources.
Okay, that second point immediately raises a critical question, and it's something our listeners wanted us to explore. Architectural trade-offs. If Deployment Manager is GCP specific, why wouldn't our sources recommend a platform-agnostic tool like Terraform, which so many people use for hybrid or multi-cloud? What is the trade-off here?
That is the crucial architectural decision right there. While Terraform is excellent for multi-cloud, using a native tool like Cloud Deployment Manager offers deep integration and simplicity within the Google Cloud ecosystem.
Oh, yeah.
For a company that is committed 100% to GCP and wants the highest velocity and the tightest integration with identity and access management IAM, a native tool often requires less administrative overhead than managing a third-party state file, which Terraform requires.
So if you know you are never leaving GCP, the convenience and deep integration of Deployment Manager might outweigh the platform lock-in risk.
It might.
But if you suspect you might need to manage AWS or Azure resources next year, the upskilling cost might be worth switching to a tool like Terraform or Pulumi now.
Precisely. It's a risk assessment based on future strategy. It's about choosing efficiency versus flexibility. And regardless of the tool, Let's address the core fear that often prevents IAC adoption,
Which is?
the destructive power of the code.
Right. When you give a definition file control over production infrastructure, it's immensely powerful.
The configuration file dictates the actual state of your infrastructure. If you accidentally delete a line in that configuration that defines, say, a production database,
Oh, no.
the IAC tool will read that change and attempt to realize it in the cloud, which means IAC tools can be used to permanently delete cloud resources if not managed under strict version control and peer review. The automation is ruthless.
That's the kind of power that keeps CIOs awake at night. That's why you need those tight controls, not just for compliance, but for job security.
Exactly.
So let's go back to managing that first risk, the unfamiliarity of the tool and that skills gap. If a team needs to evaluate its readiness for a new GCP project with a business goal of cost optimization, simply hiring external experts is a temporary patch.
It is, and it doesn't build long-term capability. You need to turn that budget spent on external contractors into internal capital.
Right. Invest in your own people.
The best practice, according to the source material, is to directly address the skill gap by investing internally and strategically. That means you must allocate budget for team training and create a roadmap for your team to achieve Google Cloud certification based on job role.
I like that it specifically calls out linking certifications to job roles. It's not just about getting a certificate, but proving practical expertise in the exact domain you're managing.
It aligns professional development directly to the business goal. If the goal is cost optimization, you need engineers certified in cloud architect or DevOps engineer roles who understand how to deploy resources efficiently using IAC.
And this manages that unfamiliarity risk head on.
It does. It ensures long-term operational excellence, and it makes the cost optimization goal achievable by people who understand the blueprints intimately.
So we have established our blueprint, our infrastructure as code, and we have a plan to train our team to use it. Now, we need the assembly line to actually build the application and deploy it onto that perfectly defined infrastructure. This is the domain of CI/CD.
Continuous integration and continuous delivery or deployment.
Yes. And this is where the process becomes a predictable engine. The factory assembly line analogy is incredibly helpful here.
It really is. A CI/CD pipeline automates the journey that begins when a developer commits a code change and ends with that application running successfully in a production environment. It eliminates manual steps and human decision-making from the middle of the process.
Okay, so let's break down the two parts of the factory. Continuous integration, or CI, is the start of the line, right?
Think of CI as the inbound quality control and initial assembly section. Whenever a developer commits code, the CI process immediately springs into action.
So it's automated.
Completely. It pulls in that new code, integrates it with the existing code base, compiles it, and runs fast tests, usually unit tests and smoke tests. The goal of the CI is ensuring that when developers merge their code, it integrates smoothly, passes basic checks, and compiles without errors.
So we're just verifying that all the parts work together before they get to the main assembly line.
Exactly.
And continuous delivery or deployment, CD.
That's the rest of the factory. The process of taking that successfully integrated and tested code package, the artifact, and reliably moving it through various testing environments, like staging or QA, until it's finally ready.
And what's the difference between delivery and deployment?
Good question. Delivery means it's ready to be deployed with a manual final step, like a button push. Deployment means it automatically goes live once all checks pass.
Got it.
This step involves packaging the application, often as a container image, and pushing it to a registry.
And the centerpiece of this assembly line, the robotic arm that does all the heavy lifting and executes the instructions we write, is our core automation tool. On Google Cloud, that tool is Cloud Build.
Cloud Build is the engine. It reads the instructions, often defined in the cloudbuild.yaml file, and executes the standardized build process every single time.
Every time, no exceptions.
No exceptions. It automates the previously manual steps of compilation, running tests, and packaging the application into its final deployable form, the artifact. This standardized execution performed by a machine is what kills that configuration drift we talked about earlier.
Now let's inject a major real-world complication that often stalls projects. Security mandates. In secure environments, build processes are highly regulated. Our security team has mandated that no part of the build process, the compilation, dependency fetching, or packaging, can access the public internet. Why is this such a common and critical requirement?
It's necessary for two big reasons: supply chain security and data security.
Okay, tell me about supply chain security.
If your build process relies on pulling external dependencies from the public internet, say an NPM package or a Maven artifact, you run the risk of inadvertently pulling a malicious or compromised package that could infect your application.
Or your whole build environment.
Right. Isolating the build forces you to manage dependencies internally where you can vet them.
And the second reason, data egress.
Data egress prevention. If your proprietary source code is being handled by a build process that has public internet access, there is a chance, either through a mistake or malicious code, that your proprietary data could be exfiltrated, leaked out.
That makes perfect sense. So the default cloud build environment that operates in Google's general shared cloud space, which by definition has public access.
Correct.
So what is the specific technical solution required to ensure our build process runs in complete isolation within our virtual private cloud, our VPC?
The solution is specific, and it's critical for high-security environments.
Good.
You must use Cloud Build Private Pools peered with your VPC.
Okay, that sounds like a serious piece of machinery. Let's slow down and explain what a private pool is and why peering it to our VPC solves this isolation problem.
Think of your VPC as your highly secure internal corporate network. It's a fortress. The default Cloud Build workers are running outside your fortress on Google's shared infrastructure. A Cloud Build Private Pool is where Google provisions dedicated high-performance workers for your exclusive use. They run within a secure network segment that you control.
So we've got our own dedicated robotic arms in a separate private facility. How do we ensure that facility is locked down and connected to us?
We peer it to your VPC. Peering is essentially creating a secure, high-speed private network connection between two separate networks. By peering the private pool to your VPC, you are effectively extending your corporate network perimeter to include those build workers.
So they can only talk to things inside my network.
They can only communicate with services inside your VPC, like your internal dependency mirrors or your artifact warehouse.
So instead of the robotic arms having to go out onto the public street to grab materials, they are now inside a secure factory annex that is privately connected to our main restricted access supply room.
That's the perfect analogy. No traffic leaves the perimeter.
So this ensures complete control.
Complete control. No traffic leaves your internal network to the public internet during the build process, preventing those external dependencies and blocking unauthorized egress of proprietary data. It satisfies the core security mandate.
And the source material connects this isolation need directly to the deployment phase as well, right?
It does.
If we build our container image securely, but then we need to deploy it to an equally secure environment, say a private GKE cluster, a Google Kubernetes Engine cluster that isn't publicly accessible, the deployer still needs to be able to reach it.
It must. If your target environment, like a private GKE cluster, is locked down inside your VPC, the tool responsible for deployment, be it Cloud Build or Cloud Deploy, must originate from a secure location that can access that network.
So you need the same solution.
Therefore, you must use a Cloud Build Private Pool peered to the VPC to bridge that isolation gap. If your deployment target is private, your deployer must also be private and connected.
Once the application is compiled, tested, and securely packaged, it becomes the application artifact. And these artifacts need a standardized, secure place to live before they get deployed.
Our artifact warehouse.
Exactly. And this brings us to a major evolution in cloud operations, artifact registry.
Historically, companies struggled because they had separate registries for different things. You might have a container registry just for Docker images, then you'd use something like Nexus or Artifactory for Maven packages, and another server for Python packages.
It's a management nightmare.
A total management nightmare, especially for security.
So if we are standardizing on Google Cloud and moving away from the older container registry, and we need a single place to manage not just container images, but also various language packages like Maven for Java, NPM for Node, Python packages, and even OS packages like Debian or RPM, what's the modern best practice service?
That unified, consolidated system is Artifact Registry. This is a critical change. Its primary advantage is consolidation. It provides one centralized repository for virtually every type of build output your organization creates.
So you no longer have to manage all this disparate infrastructure.
Correct. No more separate systems for Java components versus Docker containers.
And what's the crucial benefit that elevates it above just using, say, cloud storage buckets? I mean, you could technically store these files there.
You could, but you would lose the consistency of security policy management. Artifact registry is needed because it offers granular IAM control across all these different artifact types.
Ah, oh,
Think about it. If you use a simple storage bucket, you are granting access at the bucket level. In Artifact Registry, you can define exactly which engineer, which service account, or which CI/CD pipeline step can read specific versions of a container image versus write a new version of an NPM package.
so the security policy follows the artifact, not just the location.
Exactly. You don't want to grant the same wide-ranging access to someone pulling a public Maven dependency as you would someone pulling a highly sensitive proprietary container image that runs your core business logic.
Right.
Artifact Registry centralizes artifact storage while decentralizing access control using the powerful identity and access management framework.
We've established the core components of the automation assembly line. IEC for the blueprint, Cloud Build for the process, and Artifact Registry for the warehouse.
Right.
Now, we are diving into specific architectural and procedural choices that make this pipeline reliable, atomic, and auditable. We are talking high-level best practices that separate the efficient pipelines from the chaotic ones.
And this section addresses the common scenarios where automation breaks down. And the most common culprit for breakage isn't usually the application code itself.
What is it then?
It's managing external dependencies that hold persistent state. So a classic example being the database.
Okay, let's tackle the challenge of schema changes for a web app that relies on a persistent database, like Cloud SQL. This is a very common scenario. If the new version of the web app requires a new field in the database, but the app deploys before the new field is created, the system breaks instantly.
It does. The new code can't find the expected structure. This is the classic race condition failure.
So the sequence is everything.
The sequence problem requires atomic and enforced execution. You must absolutely guarantee that the database schema change, the creation of that new column, happens successfully before the new application code that depends on it is live.
So how do we structure the factory line to enforce that order? What's the best practice?
Our source material is explicit here. The best way to structure this is to have a single unified pipeline where step 1 applies schema changes and step 2 deploys the web app.
Why is running it in one sequential pipeline so much better than, say, letting the database team handle schema updates in one manual process and the deployment pipeline handle the app in another?
Because a single sequential pipeline maintains traceability and enforces atomicity.
Atomicity.
Atomicity means the whole change is treated as a single indivisible unit. If step 1, the schema change, fails, maybe due to a syntax error, the pipeline immediately stops, rolls back the changes possible, and step 2, the app deployment, never even runs.
You avoid that brief, fatal window where the infrastructure is in an inconsistent state.
Precisely. Manual changes introduce human error and violate that IEC principle of code-based changes. And parallel or separate pipelines just create a race condition where you have no guarantee of the order of operations.
So the single structured pipeline ensures that transactional integrity.
Yes, between the application and its critical persistent state layer.
Moving from integrity to accountability, let's emphasize auditability again. In a modern environment, every organization needs an infallible way to link a running production deployment back to the exact code that created it. If a security vulnerability is discovered in a third-party library, we need to know instantly which deployed images contain that vulnerability.
This is the imperative for audits, security, and fast incident response. You cannot rely on documentation or a developer manually writing down a version number. The process has to be automatic and undeniable.
So what's the required action?
For every container image created, you must make the container tag match the source code commit hash.
So we are taking the unique identifier that Git gives to every single snapshot of our code, the commit hash, and stamping that serial number onto the final manufactured product, the container image.
That's the key. When Cloud Build finishes building the image, instead of tagging it myapp.latest or myapp.v1.2, it tags it myapp.shasha2f84a56b or something similar.
What's the immediate practical benefit of enforcing that convention? What does that get me?
Instant diagnostics. If the deployed container image is tagged myapp.shasha2f84a, an auditor or an incident response team can immediately look up that specific hash in the source code repository.
Oh.
They see the exact code that was committed, the exact developer who wrote it, the pull request review, and the exact time that code was created. This creates an unbroken, cryptographically verified chain of custody from code commit to running application.
Without this, your audit trail just breaks down.
It breaks down, and incident investigation becomes exponentially harder. This traceability is non-negotiable for reliable DevOps.
Finally, let's talk about formalizing the deployment flow. especially when verification is necessary between environments. We can't just automatically promote every successful build straight to production.
No, you need staging gates to ensure quality.
Right.
The concept is controlling the promotion of a change through explicit approval mechanisms built right into the repository. The source describes a robust flow that utilizes repository tags, which act as that approval mechanism.
Okay, so step one is moving it into the first verification environment.
You first deploy staging tags to a staging environment for testing. This is where quality assurance or QA teams or comprehensive automated tests verify that functionality and integration are correct. The presence of a tag like v1.2.0 staging tells the automation tool, this version is ready for the testing environment.
And only after successful verification does the application earn the right to move forward to the sensitive live environment.
Exactly. And the key is that the approval is signaled back in the source control system. Once testing is successful, the developer or the release manager doesn't manually deploy.
What do?
They execute the next crucial step. After testing, tag the repository for production. This might be tagging the same commit hash with v1.2.0 prod.
I see.
And finally, the automation tool is just monitoring for that specific production tag, and when it sees it, it initiates the last step. Deploy the production tag to the production environment.
So the act of tagging the repository becomes the formal verifiable gate that separates testing from production deployment.
It's a highly auditable way of confirming approval.
It creates a clear, verifiable gate.
Yes. The change is promoted only by the administrative action of tagging a tested artifact, ensuring that nothing enters a live environment without passing through the necessary checks first. It turns a manual decision into an automated yet governed event.
So we have built the process, secured the environment, and formalized the flow with tags and audits. Now we need to ensure the quality of what we are building holds up under pressure.
Right.
This takes us into testing, resilience, and stability, how we prevent bugs, reduce downtime, and ensure the application is reliable for the end user.
And testing is often the weakest link in a pipeline. If your tests are slow, irrelevant, or run in the wrong place, all the automation in the world will just deploy bad code faster.
That's a good point.
So we need to look at the hierarchy of testing and the optimal sequencing across environments.
Okay. Our sources define 3 major types of tests that should be integrated into a CI/CD flow: smoke tests, integration tests, and load tests. Let's define them clearly for our listener. What exactly is a smoke test?
A smoke test is the fastest, simplest check. The name comes from hardware. If you turn it on and it doesn't smoke, that's a good first sign.
Chuckles, right.
In software, a smoke test is a quick health check. Does the application start? Can you reach the main endpoint? Does the database connection open? It's the minimal sanity check post-deployment, designed to catch obvious, catastrophic failures.
They are critical, but they don't tell us much about functionality. What about integration tests?
These are much deeper and require multiple components to be running. They check if different system parts, like your application's checkout service and the payment gateway API, or your microservice and a shared message queue, are talking to each other correctly.
So they verify the communication paths.
Exactly. The data contracts between disparate components of the system.
And finally, the most intensive test, load tests.
Load tests are focused purely on performance and reliability under expected stress. They simulate high volumes of user traffic, thousands of concurrent users hitting the system, to check if it can handle the required throughput without crashing, running out of memory, or slowing down to unacceptable levels.
So that requires a pretty beefy environment.
It usually requires spinning up a dedicated temporary environment, yes.
Given these definitions, the optimal sequencing for automated testing across development, staging, and production is clearly laid out in the source material. Where should each of these test types live?
The optimal flow is sequential and risk-adjusted. Integration test, in dev load test, in staging smoke test, in prod.
Okay, walk us through the rationale behind that specific sequence. Why that order?
You run the integration test in dev first, because you need to verify functionality early and often. If the parts don't talk to each other correctly, there's no point in burning time and resources on performance testing. The integration test gives confidence in the logic.
Makes sense. Then we shift to staging for the heavy-duty test.
Exactly. You run the comprehensive load test in staging, because staging should mimic production conditions as closely as possible, the realistic data volume, network, and so on. This is where you verify performance under realistic expected traffic.
Because performance is the hardest thing to replicate.
It is, so staging must be dedicated to it.
And the smoke test and prod is just a final safety net.
That's the final check. Once the change is live, You run a very quick smoke test, a 30-second sanity check, to ensure the deployment itself didn't break anything fundamental during the final switchover.
Right. You're not load testing in production.
You don't run load tests in production on new code,
Okay.
and you shouldn't need deep integration tests if they pass staging. The sequence is logical, efficient, and minimizes risk exposure.
Speaking of risk, a perpetual pain point for engineering teams is when performance bugs are not seen in staging, only to hit production and cause chaos.
Happens all the time.
What's the core reason for this disconnect, given that we just said staging should mimic production?
It's almost always due to resource scarcity in testing environments. The staging environment, usually due to cost savings, often lacks the realistic data volume, the necessary network latency, or the sheer concurrent load that production sees.
So it's functionally correct, but it fails under stress.
Exactly. And if you want to adjust your procedures to avoid this recurring problem, the solution is straightforward, but requires budget. You must increase the load on your test and staging environments.
So if your production environment handles 10,000 requests per second,
Your staging environment must be capable of handling at least 10,000 requests per second during load testing.
make your staging environment hurt.
That makes the testing realistic, yes.
Okay, even with great testing, we need strategies to further limit exposure when deploying. Our sources offer 2 additional deployment model approaches to dramatically reduce the number of unplanned rollbacks.
Yes. Beyond rigorous testing, we employ strategies that limit the audience of a potentially flawed deployment. The first approach is designed to eliminate downtime and ensure quick recovery.
And that is,
Introduce a green-blue deployment model.
how does green-blue work in practice?
You maintain 2 identical parallel production environments. Green, which is the old, currently running version, and blue, the new version. You deploy and test the blue environment fully in isolation.
Okay.
Once it's validated, you instantly switch all user traffic from green to blue, typically just by swapping a load balancer pointer.
And if something goes wrong,
If blue immediately fails due to a bug under production load, you instantly switch back to green with 0 downtime. It's an instant, safe parachute.
and the second approach moves beyond parallel environments and focuses on rolling out to a small, real audience first.
That's replacing the dedicated QA environment with canary releases.
The canary in the coal mine.
Exactly. Instead of a full QA team testing a simulated environment, you deploy the new version, the canary, to a very small subset of real production users, say 1 to 5% of traffic.
And you monitor that small group very closely.
You monitor the key performance indicators, the KPIs, of that small group error rates, latency, conversion success. If the canary performs well for an hour or a day, you roll out to the rest of the user base.
Canary releases seem significantly more powerful because they test against real users, real data, and real network conditions,
They are.
something even the best staging environment struggles to replicate.
They are fantastic for catching subtle performance regressions or behavioral changes that only appear when millions of users interact with the system. It uses the lowest risk users as your final phase of testing, instead of risking the entire user base.
Despite all these safeguards, robust load tests, green-blue, canaries, sometimes a change still negatively affects a KPI and an investigation is needed.
It happens.
If the fix will take a week, we need to roll back immediately. What is the safest, most auditable practice for reverting the system?
This is a critical procedural choice. The worst thing you can do is manually intervene logging into a server and swapping in old code.
Because that destroys the audit trail.
It destroys the audit trail and immediately reintroduces configuration drift. The safest and most auditable practice is to treat the fix itself as a code change and use the system you already built.
Which is?
Revert the source code change and rerun the deployment pipeline.
Why is running the pipeline for the rollback so important?
Because the pipeline guarantees that the rollback is executed according to the exact same rules, tests, and security checks as the forward deployment. By reverting the change in your source repository in Git, you create a new commit, a new auditable event that undoes the previous bad commit.
So the rollback itself is tracked.
The pipeline deploys this revert commit, ensuring the infrastructure and the application code are deployed as an atomic, verified unit, and the rollback action itself is now tracked in your repository history rather than being an undocumented manual panic.
Let's turn now from deployment stability to application resilience. How the application handles unexpected external failures without collapsing.
Right.
If our application makes HTTP requests to an external service, like cloud storage or a third-party API, and occasionally those requests fail with transient errors, like an HTTP 5XX server error or a 429 too many requests.
These are temporary congestion issues. These fleeting errors are a fact of life in distributed systems. You should never immediately throw an error to the user if an external request fails.
That creates an artificial fragility.
It does. Instead, the application should try again, but it needs a smart strategy.
What does that smart strategy look like?
The best practice is to implement retry logic using a truncated exponential backoff strategy.
Okay, that is the most technical phrase we've used yet. Let's make sure we ground the concept of truncated exponential backoff in a simple analogy for our listener.
Think of it as being a polite customer calling a very busy customer service line. If you hang up and immediately call back 1 second later, you are just jamming up the line further, making the congestion worse.
Right, that's a dumb retry loop.
It is. A polite customer waits longer each time.
Okay.
Exponential backoff is that polite queuing strategy. If the first request fails, you wait, say, 1 second. If the second request fails, you wait twice as long, 2 seconds. If it fails again, you wait 4 seconds, then 8, then 16.
You're backing off exponentially.
By exponentially increasing the wait time between retries, you give the external service time to breathe and recover from its congestion, ensuring your application doesn't overwhelm it further.
And what does the word truncated imply in this context?
Truncated means two things, both designed for safety. First, it implies a limit. You don't want the wait time to grow to 5 hours, so you cap or truncate the exponential increase, maybe at 64 seconds.
Or the second thing.
Second, you usually add a bit of randomness, a slight jitter to that delay.
Why the randomness?
If thousands of clients all start failing at the exact same moment and all calculate their next retry for exactly 8 seconds later, they will all hit the service at the exact same moment, creating another failure wave.
A thundering herd.
Exactly. Adding randomization ensures they spread out their retries, which is critical for application resilience and system stability across the entire infrastructure.
We've covered the core assembly line and the resilience factors. Now for some final management topics concerning long-term system stability.
API versioning, efficient migration paths, and reliable job scheduling.
Yes, these are the practical, long-term considerations that ensure your system remains stable and manageable over years, not just weeks or months. Let's start with API stability. If a company provides a service, like a recommendation engine, via an API, they frequently need to make changes. But if a change is backward incompatible, meaning it would instantly break their customer's existing integration, how do they handle that?
This is API Lifecycle Management 101, and neglecting it is one of the fastest ways to frustrate or lose customers. You cannot simply update the API and expect clients to re-engineer overnight.
So what's the recommended practice?
It's a standard industry convention.
Right.
You must use a versioning strategy for the APIs that increases the version number on every backward incompatible change.
So if I decide to fundamentally change the output structure or remove a required data field, I increment the version number, say, from V1 to V2.
Exactly. And you deploy the V2 endpoint alongside V1. V1 remains stable, fully functional, and officially supported for a defined period, often 6 to 12 months, allowing customers ample time to migrate.
And new customers go to V2.
New customers are directed to V2. This provides stability, clear documentation, and protects existing customer workflows from unexpected disruptive breakage. The version number in the URL or the header is the critical boundary.
Next, let's talk migration efficiency. Many organizations are moving from legacy on-premise virtual machines, VMs, to modern container orchestration environments like GKE, but manually re-engineering every application, analyzing dependencies, writing Docker files, and managing configuration is extremely time-consuming. What is the best practice for migrating a VM with minimal overhead to GKE?
The goal here is automation and cutting out manual effort. You want to avoid the faff of manual containerization.
I like that word, faff.
The best practice for achieving minimal overhead is to use migrate to containers to deploy to GKE autopilot.
That sounds like a powerful 1-2 punch. Tell us why that combination is the best shortcut for migration.
Okay, so migrate to containers is the first key component. It's a specialized Google Cloud tool designed to analyze the running VM and automatically containerize the application environment.
So it does the hard work for you.
It looks at the OS dependencies, the running processes, the configuration, and essentially packages all that into a production-ready container image without requiring an engineer to manually write a complex Docker file. This saves immense engineering time.
And the second part, Deploying to GKE Autopilot?
GKE Autopilot is Google's fully managed mode for Kubernetes. It simplifies the operational management post-migration dramatically because Autopilot handles almost all cluster operations automatically, node scaling, upgrades, security patching.
So you cut down on both migration cost and operational cost.
By moving the application from a VM directly into an Autopilot environment, you drastically cut down on both the migration engineering cost and the subsequent operational management cost, fulfilling those cost optimization goals we discussed earlier.
Finally, let's look at reliable task scheduling. We often need to run background tasks like daily report generation, nightly database backups, or cleanup scripts reliably on compute resources. How do we ensure that if the compute service is temporarily down or overwhelmed, the task still gets executed when the service recovers? We need guaranteed delivery.
We need a system that decouples the timing mechanism from the execution environment. You don't want the scheduler to talk directly to the compute service, because if the compute is offline, the task simply fails.
So we need a buffer.
Exactly.
Okay.
Leveraging Google best practices, the architectural approach is to create a buffered, reliable message flow. You should be using the cron service provided by App Engine Cloud Scheduler to publish messages to a cloud pub subtopic, and then having the utility service subscribe to that topic.
So the cloud scheduler handles the exact time the job needs to run, the tick-tock. But PubSub is the crucial middleman. Why is PubSub so necessary in this flow?
PubSub acts as a robust, guaranteed message queue. Let's say the cleanup script is scheduled for 2 a.m., but the compute engine service running the script is momentarily down for maintenance. The cloud scheduler successfully publishes the run cleanup message to the PubSub topic. If the utility service isn't available, the message doesn't fail. It waits safely inside the PubSub topic until the compute service recovers and pulls the waiting message.
So it guarantees execution.
It guarantees delivery. This decouples the scheduler from the execution environment, ensuring that the task is reliably processed when the compute resources are actually ready and available. It's far more resilient than a direct HTTP request from a cron service to a compute service.
That was an intensive foundational deep dive into the automation assembly line. We started by ditching manual configuration with Cloud Shell, established the ISC blueprint with tools like Cloud Deployment Manager, and then built out the secure CI/CD factory using Cloud Build Private Pools and Artifact Registry.
And we solidified those practices by focusing on the procedural choices that matter most. Enforcing auditability by linking container tags directly to source code commits. Ensuring data integrity by sequencing schema changes before app deployment, and building resilience into our applications with strategies like that crucial truncated exponential backoff retry logic.
Every step of this process is about reducing risk and increasing delivery velocity.
By replacing risky manual labor with repeatable code.
This entire approach, DevOps and management, is fundamentally about taking manual, error-prone processes and replacing them with code and automation. We are formalizing the journey from code idea to running application.
It is. And as we close, I want to leave you with one final thought based on the principles we've covered today.
Okay.
If auditing and traceability are so essential for deployments, ensure you know exactly what code is running where, how can adopting IAC and CI/CD principles, not just for infrastructure, but for defining business rules and compliance requirements, fundamentally change how quickly and safely your organization can adapt to new regulatory changes?
So applying the blueprint concept to governance itself.
Exactly. Governance is code. That is the next frontier.
A compelling question to mull over. Thank you for guiding us through this essential deep dive into the foundations of DevOps. We'll catch you next time.